So we're going to take a look at Coulombic energy of repulsion and the exchange energy. In the past, we talked about Hund's rule, but just remember that we're using it to place their maximum total spins or parallel spins. And if two electrons are in the same orbital, the energy is going to be much larger than if they were in different orbitals. This is due to electrostatic repulsion. Now, for example, on the bottom you have 1 pi c plus 3 pi e, and on the right you have 0 pi c plus 3 pi e. But what is that? What is pi c pi e? The Coulombic energy of repulsion is a pi c, and the exchange energy is going to be pi e, right? Coulombic for pi c, E for exchange energy. So how do I know to get these numbers? So when we look at pi c and pi e, on the left is the pi e example, on the right is the pi c. It's pretty obvious at this point that if you can exchange the first up arrow with the second up arrow, being sure that they're a parallel spin the same direction, you get 1 pi e. And on the right example, if they're in the same orbital, they're paired, opposite direction, you get 1 pi c. The more pi c you have, the more you destabilize, having higher energy in the state. And then the more pi e you have, you stabilize the system, having lower energy. So there is kind of a little hierarchy. From highest to lowest energy, you have on the left the pi c, which is the paired. You have up and down, which is opposite. So you have no pi e or pi c. And on the right, you have pi e. So it lowers the energy state. The total pairing energy is notified by pi, which equals pi c plus pi e. Remember that you don't say pi c equals 1. You just say, I have 1 pi c, or 1 pi e. So we're going to do an example, D8 orbital. So you have 8 electrons, and you want to find pi c and pi e. Pi c is pretty obvious at this point. You have 3 paired, so you're going to have 3 pi c. Now you want to find pi e. How do you do that? There's actually 13 pi e. So first you take your first one, you kind of draw an arrow, or if you do this in your head, even better. 1 goes to the second, 1 goes to the third, 1 goes to the fourth, 1 goes to the fifth. So you have total of 4 pi e at this point. You take the second one, you do the same. Now you have 3. So you have 7 total. You do it again, 9, 10. So you have 10 pi e. Remember, that was for the up spin only. Now you need to account for the down spin, right? So then you have 3. So you have 13 pi e in total. Remember in Gen Chem that you had exceptions to these rules or principles, right? Chromium and copper. On the right, I only did copper, but that's fine. We'll use it as an example. If you were to fill in each electron, you would get 4s2 3d9, right? But in actuality, you don't. And this is a better explanation of this, is because the 4s is in higher energy state. But if you were to take that electron and put in the d orbital, you fill it up, you still have the same amount of pi c, but now you have more pi e, therefore lowering the energy state, therefore stabilizing it. And you can think about chromium. Because it's half filled, they're not as stable as filled subshells. So you want to fill them up because of the increase in pi e. And that's it. That's all I got for you. Take care.